Hi there, 2604 students. In class, we've been talking about how a transistor is a kind of multiplier of currents, but it's also something that can shrink effectively or magnify impedances. And it's important that that's in our backpack as we go forward. So I wanted to break down a detailed description of how that happens in the case of looking into the emitter of a transistor. So let me just give the detail of that discussion we were having in class just yesterday. This is the circuit that we had. So we had some other circuit that we don't really care about right now, and a transistor. And the transistor we had replaced with our small signal model. But we wanted to deal with a case where there's some impedance, ZB, that's hooked up to the base of the transistor. And the question we asked ourselves was, well, what impedance would I see if I walked up to this point right here and I put in a little test voltage, Vx, and I check to see what current Ix flows into this thing. And this is what we do when we talk about input impedance from a certain place. So using Ohm's law, this is the calculation that we're attempting to do. What I want to do in this brief chat is emphasize what we have to do to properly take care of Vx and all the signs. So if we take this one step right now, and we leave that Vx there, the easy observation here is to say, well, Ix is really actually just equal to some currents that we normally talk about in the transistor. And those currents, we have a habit of assigning certain signs. And by that, I mean the direction of these arrows. So for an NPN transistor, the base current goes into the base, the collector current goes into the collector, and they both come out the emitter. So when we look at Ix, it looks like minus the emitter current. And we know that eventually we can go and replace IE with things that have to do with the base side of the transistor and beta. And that's not so hard to do because we know that the emitter current is just beta plus 1 times IB. So we're going to substitute that in a moment. But the thing we have to take a little special care of is how do we compute Vx? When we do that, we're going to be using Ohm's law, but we have to apply it carefully, remembering the convention. So let's just have a quick reminder of Ohm's law. This is the thing that we want to apply Ohm's law to. So I've taken part of the circuit here, and I'm just putting it off by itself. Notice that even though this point that I'm drawing right here is hooked up to other things in the circuit, it's still a point we can measure with the voltage. So actually, that is the same as our test Vx. If we want to use Ohm's law, what we're talking about is exactly this. So Ohm's law is we're saying we have some element and we want to describe the voltage drop across it. So notice the delta V. We may not know other things about the rest of the circuit. We know that across these 2 points right here, there's some delta V. And if we just see this whole chunk that we've got, never mind the fact that there's 2 resistors in there, if we just see this as a circuit element, Ohm's law has a particular polarity associated with the definition. So this Z that I've drawn here, if this is my Z, it's got 2 terminals and I make a choice. I put a plus in one place, a minus in the other, and that's my delta V. But the way we define the current for Ohm's law is going into the plus. So this definition becomes important when we go and we apply it up in that picture that we have. Because if you think about this situation here, let's use some color here. This piece of the circuit that we're looking at is a single impedance, but there are currents that we actually have names for already, namely IB, so I base. So we've got a name for the base current. It happens to be assigning the other polarity. But our objective when we're computing this input impedance is to use the Vx and the Ix sort of as tools, but in the end, we're just looking for an expression for resistance. So we're going to be replacing things that we know from transistor laws. So if we go up and we carefully apply Ohm's law, we're doing it to this situation right here, where we've got this, we've got the beta of the transistor, and we're going to be able to convert the pieces of this expression into things that we have information about. The Vx and the Ix are just a tool. You have to apply the tool carefully, as I found out in the lecture. So if we take what we've just discussed into this expression, here's what we're going to find. Let's replace the Vx really carefully. We're going to use Ohm's law. What that actually means, be careful about the sign of that current. If we honestly ask ourselves, hey, what is the particular delta V that we're interested in and the I that we're interested in? If we replace what we have for Vx, what we're really talking about is minus IB. So when we look at the current that's involved inside this branch right here with R pi and Z base, we have another name for that current. It's IB, but it happens that in the definition of Ohm's law, we need the current that goes into the plus. The plus we don't have a choice about. Vx we've chosen as looking at this terminal and this terminal, and we define the voltage of plus with respect to minus as I've drawn in this picture. So when you ask yourself, okay, what's the I in Ohm's law? We have a name for that current, we have a symbol, but it happens to be minus IB. And you can get that consistently from the definition of Ohm's law as long as you remember that this is how we define that I. That I is the one that goes into the plus. So when we go back here, we say, okay, what's the voltage drop across that point that I'm trying to measure, Vx? Well, it's IB times the sum of those impedances. By being careful with the application of Ohm's law, we get the minus in there. If we now replace minus IE, well, that's actually just IB, so I'm replacing the IE right now. If I replace IE, I know it's actually just the sum of those two currents, which happen to be the same pattern of current. One is just multiplied by beta. So that's where the beta plus 1 comes from, as we've been discussing. At this point, you can actually see that we have a minus sign in the top, we have a minus sign in the bottom, and these things are going to cancel out. So when we go to finalize the expression for the impedance, we've done this in a really mathematical way by following the rules. We didn't use any intuition. And what we get is the value of the resistance is positive if that R pi and Z base are positive. And it's just scaled, it's just divided by the beta plus 1. Another way of looking at this is an intuitive way, which I can discuss in another video, but I just wanted to make sure that we laid out in detail how that calculation works and how, if you're careful in your discipline and you follow Ohm's law and use it correctly, with that discipline, the signs will come out. And it can be important sometimes when you have a complex circuit with more parts that you can't check as easily with your intuition the way we could in class. Anyway, thanks for watching, and we'll be talking more about this type of thing in the future. For example, why not try doing the same exercise but looking into the base instead of the emitter?